We welcome you all to the CHIP seminar today. When we think of the UCLA Biostatistics Department, we have some real heavyweights. And I look out and I see Tom and Afifi, and it's hard to think, wow, how can we really increase the talent pool? But actually, they've managed to do just that with our speaker today, Dr. Sudipto Banerjee. Coming in, he is the chair of the Biostatistics Department. I could talk about his many accomplishments. I know just off the top of my head, he's the lead author on a couple of textbooks, one on spatial analysis. I believe in 2012, he was elected a fellow of the American Statistical Association. But instead of talking about all his accomplishments, to me, the most interesting part is how he got into this area of spatial analysis and public health. Growing up in Calcutta, with the heavy air pollution, he experienced asthma at a pretty early age. That led to his interest in how to help people with asthma and air pollution, and he got into spatial analysis with his interest in math. He's worked with the California Health Department in tracking asthma patterns. He's worked on the oil spill in the Gulf of Alaska, tracking pollutant patterns and how to help people there. And today it's a real honor to have him share with us some of his work in public health on space, time, and gradients and spatial analysis. So without further ado, we welcome Dr. Banerjee.
Thank you. Well, thank you so very much, Scott, for this wonderful invitation and really a very flattering introduction. I'm not sure I deserve that much, but nevertheless, I'll take it. And it is really, really a pleasure to be here in UCLA and, of course, in the Department of Biostatistics. I am honored to be a colleague of people like Afifi and Tom and all my other colleagues, and also all of you here. It's wonderful. I was so happy that Scott decided to invite a nerdy theoretical statistician in some ways for this talk. But I am really, really happy and excited because I love meeting people and knowing what you guys do. And I've heard about the center from Scott, and it's really, I hope, the beginning of a wonderful relationship that perhaps we can forge between biostatistics and you guys here. So thank you once again. Yes, this is sort of the title of the talk, Space, Time, and Gradients, and why we need them in statistical modeling for public health data. And I should acknowledge my former student, Harrison Quick. He did a PhD with me in Minnesota, and he's right now at CDC. He was, I don't know whether you guys follow his work, he's actually pretty prolific in this particular area, a couple of papers with me, but then he's done some work on his own, which is also very, very nice for the advisor to see. He spent a year in Missouri, Columbia, then he fell in love, and there was a two-body issue, and he's now in Atlanta. The other author, or I should say collaborator, this is not one paper really, but Brad Carlin, who was my former boss in Minnesota, well-known guy, wrote a Bayesian textbook himself. Wasn't very happy that I was leaving Minnesota, but he's a good friend of mine and said, lesson number one, being a chair, you can't please everybody. So that's Thank you so much. But anyway, I will try to give you a little bit of an overview of this sort of project. It's, again, as I said, it borrows from a couple of papers, but it is about space, time, and gradients, and I'll explain these terms a little bit and why it's important that we've, or at least why I think it is useful. So, we live in an information age, and computers are collecting more and more data, and these data come in different types of forms and shapes. Measurements, counts, costs, sales, revenue. They arise in the sciences, in public health, in business. But obviously you need statisticians. I mean, big data or data as such are sexy words nowadays. You see them all the time in media outlets, New York Times, CNN, folks who would never be called on by media organizations are nowadays coming on primetime TV because they do something with data. Nate Silver, perhaps we all know, I mean, he's done no harm to our profession, has popularized it with bang-on predictions of electoral results. So you need statisticians, and statistics is, I think, in my opinion, an art and a science. In fact, it's much less of math, interestingly, than an art and a science. Of course, you need math, but it's a bit of an art because you really need to understand the problem and then try to use your intuition and your skills about how best to explain a phenomenon. And there is a bit of art in that. And there, of course, is the science because you need to understand what's going on in the science. So, we try to make good use of information to make sound decisions. So if somebody were to ask me the modern definition of a statistician, I would try to say something like this informally, the last bullet. We are in the business of making good use of information to make sound decisions. That's pretty much what it is. Okay, so here's a picture. And this picture is, can anybody guess what this picture is? It says space debris, but it's actually a little more specific. Okay, I'll give it to you.
Death Star and Star Wars.
That's wonderful, yes. May the force be with you. No, it is actually, interestingly, a picture of the satellites revolving around the Earth. These are all geostationary satellites, and there are that many of them, seriously. And if you count, they're actually in the thousands, and they're all up there, And
many are DirecTV.
I do not know of that, but yeah, and maybe KGB and maybe a lot of other folks are sponsoring them. I mean, they're still mostly launched either from the United States and the Soviet Union, but they're sponsored and financed by emerging countries like China, India, Brazil, and so on. And what happens, one of the consequences, several consequences of this, obviously you can, live television being one of the main things, you can watch the World Cup soccer tournament wherever you are or wherever it is played, and perhaps the Super Bowl too, and so on. But the more relevant point for this talk is that this is the reason why GPS has become as good and as pervasive as it is. So just to give you one of my interests, why I got into spatial statistics, Scott gave a very nice public health perspective to that. Another specific reason was my dad was a civil engineer, and one of the things he taught me was trigonometry, and that's one area of math in high school that I was pretty good at. And I was also interested in some spherical trigonometry, which is not taught very much nowadays because the formulas can be derived in other ways. But one of the things that fascinated me was how ships used to calculate as they move from one point to the other, their paths and so on, and map projections. And nowadays, interestingly, the whole mathematics has changed, because it's not that you are on the land and you still want to see where you want to go, chart that path. It's actually coming, the data is coming from up there, from all these places, and they send you 3 or 4 signals. There are 2 different satellite models. One is called a 3 satellite model and the other is called a 4 satellite model that actually sends beams, and this is where time also comes in. You actually measure lags and you do a fairly straightforward linear algebraic equation. You solve that to actually get your coordinates. All right, here, and then depending upon where you want to go, you get some information for that location, and it will automatically give you the chart. So the mathematics has changed dramatically. So spherical trigonometry in that sense is not used as much nowadays as is GPS mathematics. So I'm not going to get into the details of that mathematics, but it's a fascinating area. And if you come to my website, there is a paper I wrote several years ago as an assistant professor in Minnesota. It's called Revisiting Spherical Trigonometry with Linear Models. So I actually connected how the algebra that you do in linear models can actually be used to derive some of these mathematics. And if you're interested, you can, it's a very friendly article for a journal, the Mathematics Magazine journal published by the Mathematical Association of America. But anyway, we are in statistics, so there's data. So one of the consequences of this is that when you are going to collect data, you actually take your handheld device like your iPhone and you press a button and you know where you are. And of course, you know what time you're collecting the data. This actually translates into huge databases. GIS is what they're called, Geographical Information Systems. That's the database part or aspect of this whole exercise. First, you have data beaming in about where you are, and then you use that to collect data and create GIS databases. And when statisticians get into the business of trying to model such data and try to understand such data, they're called spatial statisticians, which is what most people know me by as well. It's a fairly specialized line. It's a little different from a lot of other areas of statistics. Because most of the time, for example, these data do not come from any designed experiments. They're mostly observational studies, if you will, and there is really no well thought out design. There's a lot of missingness and noise and so on. And sometimes the questions that are asked are also pretty messy. So I will give you an example of that. But just a very quick idea about modern statistics and also how space-time fits in there. So there are a number of areas in the sciences, including climate sciences, ecology, environmental health, real estate marketing. Many of you perhaps know Zillow. You go there and you actually type in your address and it gives you the selling price of your home. It's a very, very watered down version of a spatial regression model that they run. There is an anecdote about that too. When I was an RA working for my advisor, who was a pretty well-known guy in spatial statistics at that time, one of my RAs was to go to the World Trade Center, the erstwhile Twin Towers. This was around 1998, I think. And I used to work for these two gentlemen who were actually running a small business. This predates Zillow. And they were actually trying to do this, to try to predict stuff. And I programmed some stuff for them. Anyway, they left, they sold their business. And they left the World Trade Center before 9/11 happened, so they were not affected. But the guy they sold their business to was the guy who eventually formed Zillow. And now Zillow is very, very popular. But anyway, so that's where real estate marketing comes in. They're essentially faced with the task of analyzing data that not only have important predictors and outcomes that we all see in a lot of statistical modeling, but also they're often presented as maps and perhaps as data that are streaming in over time. Okay, so this is especially for satellite data, remote sensing data, and so on. So here's a very simple example. This is almost like a toy example, but it is actually a fairly serious example in public health. So if you're an epidemiologist, you may be wanting to analyze lung, breast, colorectal, and cervical cancer rates in California, let's say. And you would perhaps like to do this by county and year in a particular state. And you would have certain variables such as smoking, mammography, and other important screening and staging information at some level. And by level, I mean this could be like the county, and because it's because of privacy issues, you do not really want to go to the person's home address, and see where he or she lives. And so therefore what is often done is such data are aggregated over regions. So there are different types of spatial data, and broadly speaking, in public health, you either have this data set, these sorts of data sets that are aggregated over regions, or in rare occasions in public health, but at least in environmental pollutants or environmental monitoring and so on, you can have data where you actually know the exact location where you're measuring, let's say, a pollutant or something. But if it's human subjects, it's usually aggregated. But the referencing is done in these two ways. One is the point, exact a coordinate of where the data is coming from. The other is like a region, like county, a zip code, a census tract, from where you are actually getting information about your patients. And I just plugged in two examples. This is a map of Minnesota. These are raw standard mortality ratios of lung and esophagus cancer between 1991 and 1998 in the counties of Minnesota. There are 87 counties, and very often, you create these disease atlases. Okay, these are very popular in epidemiology, and you could create the atlas using simple raw data, just plot them. Or you could actually do some kind of statistical modeling to smooth the maps, bring out the clusters better. But one of the things that you can see is that there, first of all, from a purely medical perspective, esophagus cancer and lung cancer are often posited to be correlated between themselves. Okay, the reason being, especially that lung cancer, is often treated with not only chemo but radiation, and that radiation sometimes causes the cancer to develop in the esophagus. So if you just look at incidence between these two cancers, they are sort of related. But then there is the spatial aspect, which is actually quite interesting, but at the same time fairly complicated, because space could act as a confounder, or it could act as something else, as perhaps something that is a little more, it could be something that is driving a common factor and so on. So, if you look at these northern counties, okay, they have slightly less access to healthcare. So remember, this is actually a situation where blues are good zones, that means the rates are low, and reds are high zones. And these have been scaled, but pretty much in the same color bar. So as you can see, you can compare the two as well. But the general pattern is that the southern counties are doing a little better than the northern counties. This is not surprising because, first of all, these are the counties where access to healthcare is less. Folks don't go for as regular visits as they go in the city of Minneapolis, which is somewhere here, and so on and so forth. But the point is that these are examples of just aerial data that are mapped. And nowadays, public health professionals who collect such data are charged not only with surveillance but also statistical inference. And so they need to model the trends and correlations, perhaps over time, or to adjust for these other predictors. They want to estimate the underlying model parameters, so they will have a model that essentially will smooth those maps, but they want to estimate some parameters in that model that from the data, so that the model is sort of learning from the data. Then they could test hypotheses. And nowadays, frankly speaking, you don't really test null hypothesis against alternative hypothesis. You literally compare models. And if each model represents a hypothesis, and the model that sort of fits the best is the model or the hypothesis that you think is most tenable with respect to the data at hand. And in some cases, you might be interested in predicting observations at unobserved times or locations. So this is an example of a purely spatial problem that I gave you. I didn't bring in time at all. But let me tell you, there are a number of databases that are very interesting, and many that we are working on. So this asthma is particularly, as Steve mentioned, it's an area where I have worked in because I did have childhood asthma. Growing up in a polluted part of India. But then there's skin cancer data, there's salmonellosis, with many predictors coming from different climate-oriented or weather-oriented organizations, as well as the U.S. Census Bureau for individuals. So a lot of data that come in, with space being very, very important because there's a GIS aspect to all of these data sets. I will focus mostly on the California asthma because we are in California, but if you're interested, I just put up this data set because these are all kind of ongoing projects that we have, and if you see anything that strikes you here, you can contact me and I'll be happy to share the data and so on. Another important problem in spatial statistics, and I'm not going to, by the way, talk about this in today's lecture, but this is the one slide that I think I should present because many of you may come across this situation, and if you think this is interesting, we can have a further conversation. But the idea is this, that so for example, if you're looking at health data, public health outcomes, your data might come from, may look something like this, you have these number of people at each county who are being diagnosed with a particular disease, or may be reporting to a hospital that they're having some discomfort, whatever it is, okay? So this is count data. But this outcome could perhaps be related to some socio-economic summaries for each county. So there would be a regression between this and this. That's fine. They're all in the same unit after all. But where it becomes interesting is pollutants. Pollutants usually come in as dots, such as these. The bigger the dot, the more the pollutant level at that location. And these are monitoring stations. So now you want to actually understand the relationship between this, and this is much harder because what do I do? How do I align these points? How do they correspond to these outcomes? Okay, that's no longer clear. So for example, there are 43 people who have reported some discomfort, some disease outcome from this county, but there are 3 monitoring stations here. Should these 3 be aligned with this? Should this one be aligned? This is pretty close. But you know, there's a lot of ad hocness here, and there are purely algorithmic versions of this where computer scientists run very, very straightforward, simple regressions, but run many, many of them, and then somehow bring out something you know, that they seem to like the best, whereas statisticians would like to, you know, try to formalize this a little bit and try to see how we can align this in a statistical way so that the uncertainty involved in such alignments are there. And a similar problem arises here, which because nowadays a lot of people are looking at health outcomes and trying to regress them on weather variables, climate, and they come from remote sensing or computer models that actually evaluate, let's say, something like temperature, but that would be mapped as a whole image in very, very fine grids. Again, you have the same problem, grid to grid, or rather region to region, but here the region is a fine grid, whereas here the region is an irregular location. So this is known as spatial misalignment, or the change of support problem. And you know, there's been some work that has been done, but this is still a pretty open area of research. More can be done. Okay, I'm going to move on to the space-time data analysis, and for the rest of the talk I'm going to focus on this. So it is the importance of where and when in statistics. Now obviously we all live in space and time, right? Albert Einstein told us that, and in a formal way. But the question is, in statistics, space and time become important when there is something, when there's information that is actually contained in space and time. Perhaps data are correlated across space and time. If you ignore space and time, you might be missing out on accurate inference. You may be getting biases. You may be missing out on a confounder. Those kind of things. Okay, so that's where spatial-temporal statistics come in. Broadly speaking, before this Harrison's dissertation, I should say, we worked, or sort of, the literature focused on 3 scenarios of space and time. One is called continuous space and discrete time. And what do I mean by this? I'll explain. So obviously, in general, space and time are both continuous. Okay. But when you get data, you actually get discrete data from both. I mean, after all, you cannot get data everywhere, and you cannot get data at every millisecond. So, but the question is that when the inference that is called for, that the statistician wants to carry out, if that inference is over discrete time, meaning let's say monthly temperature data. Okay, so this data comes from many locations, perhaps across the United States, but they are like January temperature, February temperature, March temperature, and so on. All right. Now, if you are interested in predicting temperature for the next month, or the next 2 months, or the next 3 months, or perhaps the next 500 months, it's still going to be continuous space, discrete time, because you are not dealing with the temporal resolution at any finer level than month. So it's month. That's the question, that's the resolution you're interested in. Let's keep it discrete, that's fine. So this is the literature that talks about that. Why continuous space? Because temperature, interestingly, when you think about it over space, it exists everywhere. And you may want to actually create temperature maps everywhere. So you want a whole map in continuum. So that's why the inferential question, rather than the data, defines or drives this description: continuous space, discrete time. Okay, here's another example: continuous space, continuous time. Now take directional wind data. Well, again, wind velocity, okay, this is actually continuous, and in fact, interestingly, it does vary quite a bit at fine temporal resolution. So the velocity that I measure here may be pretty different from the one that I will measure in the, 650 Charles Young drive, even though they're not very far away from each other. And you would actually like to perhaps create velocity maps continuum in space, but you also want, because it actually changes at a very fine temporal resolution, you may want to actually have a movie of how the wind velocity changes over time. So that's why it's continuous time. Discrete space, discrete time, this is actually very easy. Yearly asthma rates across counties, very common in public health. 90% of data in public health are naturally discrete space, discrete time. Discrete space because, as I said, patient privacy does not allow us to do anything more, and discrete time because you probably like to go every month, strictly speaking. The fourth case, which actually Harrison dealt with and which I'm going to talk about, and there's some ongoing work on this as well, is discrete space continuous time. And here the example is like daily asthma rates across counties. Now why is this continuous time? So across counties, discrete space is fine because county, 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 county. I don't need points inside counties. That's not of interest in the inferential question, at least here. It's more about the policy making. They want to know the rates by county, so that's fine. The data is at the county level, the inference will be at the county level. So discrete space. Continuous time, because it turns out, and this is something that I worked with the California health agencies, that they actually do have daily data. But the problem is that the daily data is exceptionally messy. There are many, many mistakes in data entry. They come from hospitalization, hospitalization rates. So the hospital folks actually keep track of the daily record, or try to, but it's a huge mess. So there's noise at many, many levels, right from data entry to data reading to so on and so forth, even classification and so on. So they hardly want to give out the daily data. What they do is they aggregate it over time with the hope that, so every month perhaps, and they look at the monthly rate of hospitalization from asthma, and then they report that. But now this problem that they brought to us was that, okay, look, I'm going to give you the monthly aggregated data, but I want you to interpolate for me the daily data. And I will trust your interpolation, quote unquote, more than the actual data that I have observed because it's really messy. Okay? I am not a health policy guy. I'm not an administrator. Many of you probably know this more than I do. Whether that is a wise thing to do or not, I will leave that judgment to you. But this was a problem that they brought to us. But they obviously, the one good thing was that they wanted uncertainty estimates when we actually constructed that, and they could validate somehow. Maybe they had some reliable days, so they would be able to validate for those days whether our method was working or not. But this seems to be a sort of an interesting problem. Okay, you have observed it at a particular resolution, the data, but then you want to do inference at a finer resolution. And what would be one way to do that over time, keeping in mind that the data is in fact correlated over space or across counties. Okay, neighboring counties will be more similar to each other than others. So this we found was actually did not receive much attention in the literature, and it actually naturally flowed into Harrison's dissertation, and he was happy and I was happy, and we had an interesting problem to work with, and it actually led to some more interesting questions that often is good, and we got it going. So here's, for example, the data set. So there are 58 counties in California. If you ask me to name them, I will not be able to. I'm just 4 months old in California. Maybe Afifi knows this in the on the fingertip. And you have aggregated monthly data from 1991 to 2008. Okay. Now, interestingly, I could give an entirely different talk on this, but one point to notice is that this is also big data in some sense, because 58 times 216, you have some tens of thousands of space-time points, and these models are typically pretty expensive. So they may not be like Walmart data in millions, but it's fairly sizable. So it's what I would say a moderately large spatial-temporal data set. I won't say it's massive. There are bigger spatio-temporal data sets, but this is one of the common phenomena that you encounter when you actually look at space-time data set. Because you have two dimensions, space and time, the data tends to explode, the size, pretty fast. Okay, and you often convert to rates like 1,000 residents and so on. And so, as I said, the question is that they have the data at the monthly level, aggregated monthly. But can we reconstruct these hospitalization rates at a daily level? So, and the other question is, can we estimate rate of change in hospitalization rates? So in other words, you can go month to month. Okay, this month this was a rate, next month this was a rate. But on a daily basis, they want to know if there are certain times of this year where this flow of patients increases or decreases more rapidly or less rapidly. Why would you be interested in that? Simple hospital management. Many of these hospitals actually, according to what I've been told, maybe some of you know better, they hire a few permanent workers, but a lot of temporary workers who actually sometimes are hired on a daily basis. And they want to basically understand the, like plan the hiring process based upon these rates of changes where they expect to see bumps. So these are some of the questions that they wanted to ask.
Actually,
Yes, go ahead.
Both Tom and I
Yeah.
are on the advisory committee to the California Health Interview Survey, CHIS.
Oh, wonderful.
So you aren't just joking, there is actually a connection, and they collect data by county.
Right.
So I can tell you more about that.
Sure, yeah, I will be interested actually. Absolutely, what they do. This is very recently I've gotten into this. I got a phone call in Minnesota actually from the California Health Department that we have this data set, would you be interested? Literally, that's how it started. So I don't know why they would call all the way to Minnesota.
Is there any variation in how they collect it that would inform this?
Yes,
Estimates.
absolutely. There is you mean variation in the way they collect this information?
Yeah, so like some start in the middle of the month to the next middle of the next month, some start, like unless there was variation in how it was reported, how would you ever make these estimates?
So if you notice, this actually starts January 1991 and ends December 2008. I am sure you are absolutely right. There's a lot of variation in the way it is actually covered. This data is collected and so on. But for the purpose of this particular analysis, we did not get into that. Our whole idea was actually to try to smooth out the entire disturbances and try to provide sensible inference, at least with uncertainty estimates and so on. But this goes back, and after 2008 also they probably have data. They release only this information. So this is what 16 years or 17, right? And so that was what basically we had, and they just gave us the monthly aggregates. They would not release the daily data to us, perhaps because of temporal, identifiability issues. Go ahead.
Well, I was going to just following up on Mary Jane's question, which I think might have been that if you're wondering whether when there's a full moon or something like that, is there a spike in rates, how would you be able to, I guess a full moon, you actually would have this external thing, but the question would be, where would the...
How would you identify the variability?
Oh,
I see, yeah.
Like
How would you get daily
a
variation?
within month effect, is that what you were getting
Yeah,
at?
how could you get variation within a month to predict the daily rate if there wasn't some data?
Information. That's an excellent question. There will be some information at the daily level, but those are from sort of like pollution variables, like we had asthma, for example, that was observed, not asthma, ozone, okay, that was actually monitored daily, and we got that from the California EPA, I think. They have a, is there an entity like California EPA, or am I misspeaking here, right? Yes. California Air Resources Board, exactly. And we used that data to try as a predictor, okay? So there was some information there. There is one, I'll show you some results, but there are 3 or 4, a couple of technical papers that were written actually on this, where, remember I just spoke about misalignment? There is a natural misalignment there as well. Now we have temporal misalignment, monthly aggregates for the hospitalization, yet daily levels for asthma. Again, daily levels for ozone. Sorry. Okay. Now you see, so I'm not going to get into the technical details for that, but there is information that you're asking. Absolutely. Otherwise, it would be a completely hopeless problem. Yeah, you have to go by rates. But there is something. Even then, it's a pretty hard problem because you don't want to just base yourself on that one additional variable. Yeah. Okay, so I spoke about this. We need to operate at a resolution much finer than that of the observations, and therefore we could not use this as a discrete space, discrete time problem, which could have been fit even in SAS or R packages. Nowadays it's fairly routine. So here's a quick look at the data set. So 19, and these are known as choropleth maps. And these are like spatial histograms, essentially. Each county, very simple. You look at the raw asthma hospitalization rates per 1,000 individuals, and here is a color bar that actually have binned the values, and you have a color code here, and you can see red is bad and blue is good in terms of in the sense that red means higher asthma hospitalization and blue means lower. And one thing that you can see is that asthma hospitalization rates have gone down over the years, or in general. I mean, I think even this picture will tell you that there's much more red in the early 90s than in this last row, the second half of 2000. Several reasons for that. Yeah, go ahead.
These are per 100,000 or something?
Per 1,000
So they're all the
individuals
same
in the same scale. Yeah, all in the same scale, exactly. And there's several reasons for that. One obvious one being inhalers and other gadgets that folks can buy off the shelf and actually use at home. Remember, these are as hospitalizations, so these are fairly serious cases. Okay, but just perhaps, California has done a much better job in trying to control pollution as well. Okay, and they have. I mean, at least Los Angeles, if I'm not mistaken, is one of those counties which, in fact, has shown a dramatic improvement in pollution rates, pollution levels compared to what they were several years ago. But that's pretty much it. But what happens here is the big data part. So see, you have these maps here, but now if you want to do this per month, okay, you suddenly have these many maps. And if I just say, hey, here's my analysis, go take it and figure, folks are not going to be very happy. You're a statistician after all. Come on, So all right, we have to do something to bring out all these features somehow and summarize them in a nice, neat way. And then there are many covariates. Here you go. Thankfully, I had the ozone level as well. But there are some factors that are at the same spatial level as the rates. So, for example, the percentage black in the counties, the percentage of young people under counties, children's asthma. Children suffer more, and so that this is an important covariate in some sense. So, as I said, there are many sources for this data, including the Census Bureau. Some of these obviously vary spatially, but really not that much temporally. These demographics they are slow moving, so they don't change as much. Ozone level, as I said, and that was an excellent point that was made, this in fact is available at a very, very fine resolution. In fact, even within a day, you could actually look at different time zone, temporal zones for ozone, even within a day. So there was a misalignment problem, but we actually were able to resolve that. I won't get into the details of that, but this is an important predictor that actually is available to us at a fine resolution. If you were to consider them on a monthly basis, though, here's how they look, just the average. Ozone, they move, and you can see the seasonality in ozone. That's the only reason I present this. This will have a little bit of an impact later on, and I will show you that, which was an interesting finding. Population density, look at this. How interesting is this map? Here's LA and there's San Francisco, and those are the two red dots probably, and then the rest is all, this is after all relative. They're all in the same scale. And then you have some variation in percentage black and percentage under 18. Okay, a little bit of the modeling. So if you are not someone who has an appetite for these sorts of notations, especially after a good lunch at 2:30 p.m. here, don't worry, I won't really harp on this because you're not even going to take away. If I was sitting in your place, I wouldn't take away much from these mathematical formulas. But let's just look at the general idea here. So here's a response, and the way you write down the model, this is perhaps something useful, even if you're not a statistician, to at least try to see how a data such as this can be cast in a model like this. just this part. So you have y sub I of t. Now I put the sub of I as index because I is the spatial county, index is the spatial county. So it's in county I, and t is in bracket because I want this to be a function of time. Remember, I'm talking about continuous time now, since I need to go to a fine resolution. So there's some thought put into this notation. Whenever you read a statistical paper and you see a notation, if it's a good, well-trained statistician, he would have put some thought into how he wants to use the notation. That's the one thing I think we teach. I remember, I know I'm talking too much, but this is a joke I must say. One of my students in my exit interview, he was a really funny guy, smart guy. He works in a pharmaceutical company now. In his exit interview, my chair, erstwhile chair, asked him, so what did you learn in these 4 years in statistics? And he said, just to write notations. Write clear notations. And my chair said, yeah, that is actually not that easy as it sounds. So, and he said, yeah. So that was actually quite an interesting answer, that all he learned was just how to write notations. So this is what I'm doing here, in fact, and I hope it will make a little bit of sense. So this is basically indexes the outcome, asthma hospitalization rate. There is a trend, a large term trend, which is usually a regression with some of those covariates that I told you. Now this is where, okay, she's gone, but this is where basically that ozone would have come in. And it is critical that I write these covariates. Oh my God, this is sensitive. I can't touch it. This is where this notation becomes important, because notice I am actually trying to keep each covariate, even if it's like some of them are percentage black or so on, there will be constants, but at least conceptually they could be observed at any temporal resolution, so that I can use covariates that are observed at the daily level to actually learn more about the so-called process, and then look, I will, no matter what covariates I have, there will be more variability and so on, which I need to capture. And so all good statisticians, what they do is, after they have taken care of some regressors or predictors, they put in random effects. The only difference here, and many of you are familiar with random effects modeling, the only difference here is that the random effects are in fact spatially indexed functions of time. So this sounds fancy, but it's nothing more than saying, all right, just like y sub I of t is an outcome that is a spatially indexed function of time, so will be my random effects. That's it. All right. And then you have this tau squared I, which is the variance for the measurement error. So think about this like a linear regression model, but with a little bit of tweak about a random effect, and there is this correlation that I need to model. If you are interested in not modeling the y sub I of t, or the outcome, as a rate, but rather as a count, you are most welcome to do that. Statistical technologies have evolved way more than they were when Afifi was in grad school, for example, and now you can simply use these in GLMs. All right, these types of models can also be fit fairly routinely. So this G would now be the logistic kind of thing, or maybe a Poisson regression, and wherever there is the link, you transform the mean, you actually plug in whatever you have here. So the key point about modeling the ZITs, which I'm going to focus on, is that for neighboring regions, these functions will be similar. Okay, rate of change. Remember, they asked about this. Now this is an important question, and this is also a bit unusual, I think. So the idea is that, all right, let's go back to calculus. When we looked at calculus in high school or whatever, when you had a function, you would actually, to get the rate of change, you would take z sub I of t at any point t naught, calculate the finite difference, that means t naught plus h. This h could be the next day, the next month or something, and you could compute this finite difference, okay? Now, if you're a statistician, you could actually compute these once you have estimated the z's, okay? The problem is that this h could be pretty small, depending upon your scale. You could rescale, but it's not a very ideal situation, and there could be numerical computational inflation. And so that means there would be overflow, and your computer would crash, and you would get a stupid result. So one way to actually avoid this is to actually go to the limit, which is what physicists do all the time, and many others, and take the limit of this. And if I can actually calculate this guy without really calculating this finite difference, then I would be avoiding a lot of pain in my computing. Why are they interested in these quantities? So as I said, let's start from the bottom here. Helps in policy formulation and hospital administration. That's the example I gave. There is also the fact that these gradients or rates of change actually are better identifiers of lurking factors or covariates. So when they look at this analysis, they might say, you know what, maybe I'm missing these variables that could explain some of these variations that I see in the rates of change. What are variables that are that may have operated on February 23rd but not on February 25th? Something like that. Okay, so that's at least a tool for them to look at. And then of course, if there are high gradients, as there are in a few cases, then they look at outliers and they want to know what's going on there. Okay, one of the good things about what I'm going to use is what is called a spatial process in these models. This is a simulation example, it's not real data. But the idea is that if, for example, your data comes from a sine curve, okay, and you have observed the points, this signal only at these dots, all right, you haven't observed it everywhere. I give you only these dots and I want you to actually refit the model. Well, it turns out that you can actually statistically refit a model so that the mean will pass through all the dots. So you recover the sinusoidal nature of this signal. So because this is well approximated, the gradients, or rather this is interpolated, I shouldn't say even approximated, the gradients are well approximated because you still get the same thing. So see, this is the gradient of this, but at those points, since the gradients are captured, you get, this is the cosine, this is the sine. So you actually get this, recover this, even if you have partially observed the signal. The only thing you have to remember is that these dots that you have, where you have observed the signal, they should be at a moderate resolution. If you had only one observation here and another here, then it wouldn't have been helpful. But if you have moderate data that is at a moderate resolution, you can recover that. I'm going to skip some of this stuff. This is actually from Harrison's slide, but the basic idea is, how do I model something across counties? How do I incorporate spatial association? And the idea is to actually try to look at a political map as what is known as a graph. And a graph is something that where each region will be like a vertex, and two vertices will be attached or connected to each other if one is a neighbor of the other. So by neighbor, you could say, to use a GIS software to say, okay, is this a border of this county? Two bordering counties would be neighbors, and you could start with that. The key point is that there is an adjacency matrix corresponding to California, which would be whose entries would be 0 if regions I and J are not neighbors, and if it would be greater than 0, usually taken to be 1, if the regions I and J are neighbors. And then you actually calculate another matrix, which is a diagonal matrix, whose entries are the number of neighbors for each county. Okay? And then what you calculate is this particular matrix, D minus an alpha times W. Okay, let's not worry about some of these technical issues, but if you just concentrate on this part, D minus alpha W, D is a diagonal matrix with neighbors along the diagonal, number of neighbors along the diagonal. W is your adjacency matrix. Now you see what happens is that this parameter alpha is something unknown. But if this is equal to 1, then this W is very much present in the model. And if this alpha is equal to 0, then this W completely goes away and it's only left with a diagonal matrix. So if alpha is 0, this diagonal matrix means there are no off diagonals and it's an independent model. There is no spatial association. If alpha is equal to 1, then W has maximum weightage and you actually basically get a lot of spatial association. So the idea would be to try to estimate this parameter and say that, all right, to what extent or what is the strength of spatial clustering that I have here. This is the basic idea about these sorts of models. Now there's a reason why this particular matrix is useful. There are many reasons actually, but one point is that it is what is called a positive definite matrix, or it's actually a variance covariance matrix. So I could assume that my spatial random effects follow a normal distribution whose variance is the inverse of this matrix. And that's a perfectly legitimate model and a widely used model, something that is coded up in a number of software, and you can estimate the alpha from your normal likelihood as you usually do. This alpha has to lie between a particular interval for this to be positive definite, so you bound this somehow. If you are a Bayesian statistician, we use prior distributions, and we say that the prior will have this, must ensure that alpha lies between these numbers. If you're a frequentist statistician, you would do constrained optimization, restricting this parameter to a particular interval. But either way, you can actually solve that. The reason why this comes out is like this. If you take the random effect corresponding to any county I, and then you actually look at the neighboring, at all the other counties, okay, the conditional density turns out to be a normal distribution with a mean which is a weighted average of the values of the random effect at only the neighbors. So in other words, I given everything else is equal to I given its neighbors. That's a huge condensation. So this is a kind of an underlying assumption for a statistical model. You have a random effect, you look at neighbors, that's all you need. You don't need to go beyond the neighbors. All right? So that actually helps in computation and in sparsity and in clustering. Many of you are probably familiar with something called k nearest neighbors clustering, right? Or k nearest neighbor means. What does that do? Or even Zillow, for example. It looks at your location and it looks at your neighbors, and it tries to find folks who have sold their houses among your neighbors. All right, and it just averages and gives you that value. Well, that average is just here, but as statisticians, what this distribution does is actually adds an uncertainty term here. So therefore, we can actually say, all right, you can get the mean, but hey, you know what? I can also tell you the uncertainty associated with that point. So that's perhaps what it is. Okay, now all this is a function of time. So this is like what is continuously evolving over time, okay, because these are all functions of time. And things start getting really technical at this point. Until this point, frankly speaking, if you're a statistician, this is pretty much well embedded in the literature. I may have skipped some parts, but Google, you'll find a lot of models like this. But getting this thing as a continuous function of time becomes a little technical, but I'll give you the flavor. So now we are actually trying to model a lot of dependencies. Let's take two regions, 1 and 2, all right? And let's take 3 time points, T1, T2, T3, where the data has been observed. Okay, even here, what I have to do is look at the number of dependencies that I will have to look at. The first row, wherever there's a bar or kind of the straight edge, that means there's some dependency. So the first row basically shows temporal dependence within region 1. Asthma hospitalization rates over time will vary, right, in each county. So in county 1, this is the dependence. The second row similarly models temporal dependence within county 2. Okay, then if you go vertically, then you basically have dependence between county 1 and county 2 at time point T1. There will be dependence between county 1 and county 2 at time point T2, and so on. And it will proceed like this. And then you have these crosses, which essentially means, well, even the value of the outcome of the random effect at time 1, region 1, would be correlated with time 2, region 2, and similarly the other one, and so on. So there are a lot of dependencies in these. If you ignore some of them, you can. Sometimes it doesn't matter, but it could matter, because these data structures are complicated. And if you can model this whole thing, then you actually get much better, much more reliable estimates, so to speak. So I'm not going to obviously tell you, you've seen enough math for the day, so let's go to the results in the last few seconds. But let me just say this much: there are very nice and not too technical ways of modeling this sort of thing. You need a little bit of linear algebra because you need a kind of a matrix, and you multiply that with these random effects to create correlation structures. But it's nothing that is very non-standard for even in the MS statistics or biostat courses. The tools are there to actually go ahead and try to model some of these complicated results. Okay, so why this mathematical madness? So one of the things that statisticians like to do is fit several models, some simple, some complicated, and then they try to do some kind of model comparison. In other words, they want to know how good a particular model fits a particular data set. So we actually fit a very simple linear regression model. What if you came and told me, you know what, you're crazy, I'm just going to use ordinary least squares regression. Forget it, nothing else. And yes, I'll take away all complications out. Take monthly data, take monthly outcomes and per county, ignore spatial association, ignore temporal association, simple linear regression. Well, you can fit it. And you will obviously be losing a lot of information. Some of the covariates you cannot use at the daily level, but that's okay. I mean, you can simplify. So there are a couple of numbers that I want to tell you. First column, PD, is a measure of how complex this model is. Because there are some, this essentially is a representation of the number of parameters in the model. Because we had interaction effects and some monthly effects and so on, it does go up to 79 parameters approximately. The DIC measure is a measure that tells you how, if the larger the number, the poorer the fit of the model, accounting for the complexity of the model. Okay, and this GR is a Neating Raftery score. It is also a sort of a competitor. Some people like this, some people like this. There are theoretical reasons why one prefers the other, one prefers one to the other. But broadly speaking, here, the more negative the number is, the worse your model fit is. So I took this as a reference because you're only interested in the relative merits of these scores. This aerially referenced Gaussian process is my most complicated model that actually fits this. Okay, and this is pretty big. It's complicated. It has 5,256 parameters overall, including random effects over space and time. Remember, there are about 10,000 or 12,000 random effects. 58 multiplied by 216, whatever that number is, 13,000 something perhaps. But whatever, there's some shrinkage because all parameters don't play a role. So what this does is it tries to estimate the effective number of parameters. But even there, it's pretty complex. Okay, but even with this complexity, you have tremendous benefit in goodness of fit because these numbers account for this PD. And they still show you that, wow, you're doing much better than some of the other models. What are the other models between these two extremes? A random intercept and slope. That would be kind of just your simple random effect model, but no spatial or temporal association. And then the CAR model is a conditional autoregressive model that would assume a spatial correlation, but no temporal dependence. Okay, so each of these models do quite substantially worse than this. So therefore, if you are going to sell this model for use, why not actually test it? And you see there's a strong story behind this, a strong motivation to use these models. Okay, let me show you one other interesting thing here. So when we were actually doing some investigations, one of the models we fit here, we used only ozone, okay, a summary of ozone as a covariate. So that was almost like static, all right? And you see what turned out was asthma hospitalizations was turning out to be negative. So that means the higher the ozone, the lower the asthma hospitalization. That seemed counterintuitive to us. And we looked at the literature. Interestingly, this is a pretty debatable situation, to be honest, because a lot of studies have found no significance, but rarely have any studies found negative significance. So obviously we thought, well, what's going on? So Harrison came and said, this. I said, no, this we really need to investigate this. Solution is very, very simple. What happened was ozone and season, as I showed you in those maps, actually has a strong interaction effect. So in order to do this, the right way to do this would be to actually take ozone right here and interact with the months. All right, and if you do that, now you see that in many cases it's insignificant, which is not contradictory to the scientific literature that have designed studies between these two variables, but also the fact that in certain cases, only towards the very end, you actually get to see the positive significance. So this is a simple lesson for you, that when you try to do even simple linear regression and you see something that is not making sense, try to do something a little bit more. Or try to think what's going on. And very often it's a case of interaction effects that you may be missing. And here's the monthly effects. Some of them are significantly negative, some of them are significantly positive. Obviously, there are some socio-demographic variables that in fact have a positive impact. As I said, in particular, children are much more susceptible and are often hospitalized because they need more care. So that's not surprising. Here's the spatial association parameter, alpha. It's pretty high. As I told you, if it's close to 1, 1 is the max, 0 is the minimum. That means independence. You clearly see spatial clustering. And phi, I did not talk much about this, is basically says, it's, how should I explain this? It's actually the effective temporal range. What do I mean by that? If you look at this, say the point estimate is 1.24, so that means that the dependence that you see over time dies out after 1.24 months or so many days. Okay. Okay, and this is approximately Markovian in some sense, because it's a little more than a 1, just a preceding month that it would actually be correlated with. When you look at data analysis for spatio-temporal random effects, you actually start, again here, you look at these estimates. Again, we reproduce some of the overall pattern that things are looking better over time. And as I said, there are many, many reasons for this, including better home care or asthma management systems that patients can take home. Temporal gradients. Now what you could do is you could look at each month, each year, and you could actually look at the gradients and you could average them, the posterior means for each county, and you could see how the temporal gradients are distributed over space. And this is where things become interesting, because this is rate of change, and now you see some outlying years. And even later on, okay, here in 2007, you see much more variation in how it's changing from month to month. If you ask me, let me be honest, I am not sure what this actually means substantively. But my collaborator or the folks who we gave these results to, they were very excited, and they said we really need to keep these and understand this better as to why we are getting these fluctuations. You could look at temporal trajectories. Here's Los Angeles and San Francisco. You could do it for any county you want. I'm just giving you a snapshot. These gray zones are the uncertainty estimates, but this is how the asthma hospitalization rate is going on, and it's easy to look at some of the spikes. And if you look at some of the spikes, here's the spatio-temporal random effect corresponding to this jump. You will have a significant gradient. One point, this is a bit subtle, is that just because there is a spike in your spatio-temporal random effect does not necessarily lead to a significant gradient effect. That is why we need some of that theory to understand how we can predict gradients with uncertainty. This is a pretty non-intuitive result in spatial statistics or temporal statistics, that the level of your spatio-temporal function is stochastically independent of the gradient for that function. It's remarkable, but it is true. So this is kind of interesting, and folks want to know what's going on. So these would be the outliers that they would come and say, oh, okay, what's going on here? And in any case, sometimes they will find an explanation, and they will try to see if there is some seasonality, and perhaps try to keep this record to try to update their hospital management administration policies. You can zoom in, and we did that for Los Angeles County because we found something interesting here. This was selected due to the presence of a significantly positive gradient between November and December from these maps right here. and we moved in here, and basically we tried to see, here were the true values, by the way, and this is the continuously interpolated value. So it's not doing something that you wouldn't expect it to do. It's basically trying to fit a smooth mean as it makes its way through these little points. These are the daily data. These are the monthly data points that you have. So from August to September, there were we actually calculated the gradients, and they were much higher. So that obviously was, if you look at a monthly resolution, you see far more a jump pretty much in September compared to August, and this happens not in every county, but by and large, it does happen pretty much everywhere. So this is a jump that is plotted for each year from August to September across each county. So in other words, the point I'm trying to make is, if you notice, even from the snapshot, we have been able to provide a large number of, I should say, analytical outputs to our clients. And we have done this in a reasonable amount of time for a fairly rich and large database. And it has, of course, needed some smart computing. But with uncertainty estimates, a full statistically rigorous, principled, whatever you call it, analysis is desirable in many, many cases when folks want to not only understand what's going on, but also in trying to formulate policies and so on. I think there are some concluding thoughts here, but I think I'm going to stop, and if you wanted to have any discussion, I'll be happy to discuss. Thank you so much.
Thank our speakers. Any other questions?
Tom.
It was interesting that you paused on the gradient data to say that you weren't quite sure what it meant tonight, because I saw that 1993 in red. And I thought, oh, that's interesting.
You were talking about
exactly that.
Oh, this one?
Yeah.
Ah, yes.
And I guess the a challenge, I suppose, to a modeling statistician is, how do you know that's not an artifact?
Oh, brilliant! Yeah, you're absolutely right.
All right, you can stop now. That answered my question.
No, that is absolutely true. Very often, I'll let you finish. You're absolutely right. This is absolutely a point. Part of spatial statistics is to produce smoothed maps so that patterns come out better. And epidemiologists in particular, in this situation, perhaps hospital administrators, health policy managers, could actually go back, look, and try to say, what are we missing that should be incorporated, even if in future we want to do a simple linear regression model. I need some variables. What variables should I go and get? So complicated analysis, spatial analysis, often leads to a subsequent simpler analysis when folks understand, you know what, there are certain variables, covariates, predictors, whatever it is, that could have explained this. Let me go get that, and I'm then going to fit a simple linear regression model. I'll still do better than I was doing with my previous simple linear regression model. And so I do not know and I think most spatial statisticians, frankly speaking, will not be able to tell you all the artifacts that may be coming up, But what is important to, I think, appreciate is that even producing these maps in a statistically principled way is rather is not trivial. And if we can provide these outputs, it's a tool that epidemiologists and HPMs can actually look at and say, you know what, yes, this is useful. So that's the point. I think you're right. This could be for many, many reasons, even for that matter here. If you look at spatial-temporal random effects as well, there is some variability here in 1993. But the remarkable thing is that theoretically, just take a look at 1993 here, since you brought up 1993. This map, in some sense, is uncorrelated with this map. Because gradients are a completely different story. And gradients started receiving attention I would say in the mid-2000s. You know, spatial-temporal random effects such as these, for example, my colleague Brad Carlin, who I mentioned, he had done some work in the early mid-90s, I would say, on this. But folks were saying, you know, it's hard for me to understand what's going on, especially given these are temporally averaged. From these maps, I would rather like to look at some of these finer details and try to see what's going on. These really deep red counties that are actually have more average fluctuation. All right, so these effects are brought out much better in gradient maps than in pure random effect maps. And it could be useful, it may not be useful. That, of course, is the bigger picture. But in certain cases, it is. It is very useful, and folks have written papers based upon these sorts of maps to try to draw something more substantive. Yep. Yes, please, Scott.
I was going to say, thinking about looking at things in a finer gradient, some of the work we've been doing here at the center with Nithya Ramanathan, who couldn't be here today.
Okay.
But work with Dallas and I on mobile phones where we
Yes,
collect
yes.
data. And so it's temporal and spatial. And sometimes for whatever reason, maybe people turn off their phones or
Right.
don't necessarily trust the data.
Right.
Thinking about, we have a lot of data, but we want to look at things at a fine gradient, but we don't always have the information at that fine
Right.
gradient.
Right. So I think it's related to this problem in the sense that, you know, you also have missingness and you want to somehow impute or interpret. That's what statisticians do in any case, you know. In fact, you will appreciate this. I was once giving a talk in Michigan, and Rod Little, somebody else asked me a question, and I said, yeah, so this is actually a missing data problem. And Rod said, all problems in statistics are missing data problems. So anyway, coming back to this, you're absolutely right. You know, this is essentially a process-based way to tackle missing data problem over space and time. And I think it's remarkable how this Gaussian process, some of you may not have heard of this, some of you may have heard of this. It's a tool that has really become hugely popular over, I would say, the last 20 years or so. And there's this parallel line of machine learning where folks always use that as well for different reasons. But it is remarkable how well it actually functions. It's pretty robust. It's kind of like a tool that can model, a stochastic tool that can model an unknown function. And that's what we are using to bring in temporal dependence. And so that's one of the advantages. If you use that, you know, you're in your setting, I think you could find some pretty robust results that would be pleasing to the eye as well.
There's a question back there.
Regarding the ozone data, how you use it? You average?
No. Yeah, you're right. That's the part I did not want to talk about. That's a different talk. Ozone data are actually available on, I think, an hourly basis.
Monitor, yeah.
Yeah.
And monitoring station level.
Correct.
Many monitoring station.
Correct. So what we have to do in this particular setting, I did not actually show that. That's a different talk. There's a misalignment. So ozone data, first of all, are arising from points, right? And they're observed at an hourly level.
Right.
Whereas the outcome I'm measuring is observed at county level and at monthly level. Right. That's remarkable, right? But if I don't use the fine resolution of the ozone data, as Mary Jen pointed out and Tom clarified, I would be nowhere with this. So therefore, there is a complicated hierarchical model that actually maps the two. I'm happy to talk to you later about that, but but essentially I need to align them in a statistical way so that I can regress, and I can actually, in the end, provide my client with something like this. Where's the table? Oh, I'm going the other way, sorry. Like this. See here, you know, when I'm presenting the ozone, I'm actually presenting summaries over interaction from the main effects. Okay, but there's a lot that goes on before I can really come in here to align the ozone with the hospitalization. Yeah, And unfortunately, I won't have time to really go through that. But that's a very good point. And anybody should have asked me that okay, how's this? I did not cheat. There was one slide I showed much earlier, which was here, right here. This is the problem that I was talking about that actually we did solve in this particular case. Ozone comes from monitoring stations.
Right.
Okay, this is only the spatial part, but there's a temporal part too. Ozone was observed hourly or maybe I don't exactly remember, but even within a day. It was finer than a day, whereas the outcome was monthly. So there are two different papers also, by the way. We had to analyze that differently. One paper concentrated on this, and the other was a bigger model with everything.
But
Yeah.
anyhow, I was trying to
Yeah.
say, some of may be explained by how the data was used, ozone data was used.
Yes, that's a very good point. You have to be careful because that's your most important predictor when it comes to figuring out about the resolution at the daily level. Yeah.
But that might actually relates to a comment I was thinking of making is that, one of the aspects of that artifact question I asked is that, well, maybe some of that, prediction is just from a Gaussian assumption, and that how does it really align with the reality? Does it tend to reproduce the kind of phenomena that are at a finer level that you wouldn't otherwise? I was thinking of I was actually thinking at first of there being sort of local people who were collecting their own data that weren't necessarily, but you could then calibrate, you could sort of calibrate the model or see how well it's predicting something external that wouldn't necessarily be well fit because it wasn't used in the fit. And it might be, I don't know, I'd be interested to understand better that process that you just described. Because because I think that it could provide explanation for some of these goodness of fit.
Yes. You're absolutely right. There's there are uncertainty estimates there as well, and of course there are assumptions. They're all. I'm not saying that this will be the gold truth, but it is at least a. This is not a gold standard, I should say, but at least this is a principled way to address a fairly difficult question. Sometimes which would apparently seem impossible with the type of data we have. Yes, I will be happy to perhaps give a more technical talk one day on how we actually merge it. It's again a missing data problem. You go to you just treat these two exactly, and then try to do that. It's a computation that becomes interesting in that case. There's a particular way in which the Gibbs sample can work out. But you're right. I certainly do not deny that. Yes, please.
Could you give the references that you said?
Yes. How best to do that? I should have actually added the references. So this is based on. If I were to give you one reference, there's a paper in the Annals of Applied Statistics in 2013, Quick, Banerjee, Carlin. Okay, Annals of Applied Statistics, not the Annals of Statistics. That's a very different journal. You may think you're in the wrong hotel if you went there. There's another paper that is just accepted in biometrics. Again, the same order. Quick, Banerjee, and Carlin, that actually also talks about some of this. And the third paper that is tentatively accepted, I don't know when it will be accepted, there might be one other round of revision in JRSSC, Applied Statistics. So in any case, the one that you can easily download or is available on the web is the 2013 paper. Take a look at that. The others, I can send you a copy if you just drop me an email. Okay. So. Yes, please.
So in your model comparison,
yes.
where you report
yeah.
different models, I'm curious how you got to the zero to be
your
model to, so are you saying that you're error-free?
No. Thank you so much for pointing that out. You see, these numbers, whatever you compute, they only make sense, at least to me, if you take the difference. So for example, I was comparing only these two models. I would make this 0 and put a 5,500 for this. So because this is my benchmark model, or sort of, not benchmark, but at least the proposed model, just for comparison's sake, I just put this at 0 and just calculate the differences and presented it that way. That's just the way I do it, you know. You could put in another number, the real number here, and then add, but it's the difference that you're really interested in. Yeah, yeah.
Let's thank our speaker.
Thank you, thank you.